Welcome to the MuAnalysis video on scanning acoustic microscopy. MuAnalysis is an electronic materials laboratory. What is scanning acoustic microscopy? Think of it as an ultrasound for ICs where the sample is immersed in water. It is a non-destructive way to evaluate packaged ICs and flip chips. Acoustic microscopy is a time-of-flight measurement. We will discuss this later in the video. Scanning acoustic microscopy is useful for detecting voids, delaminations, and cracking. There are two modes of operation, reflection and transmission. The blue line represents the water line below where the device is immersed. Looking at the left image, in reflection mode, the signal is sent to the device and the reflection is received and analyzed. In transmission mode, the detector is located underneath the device. Some systems can operate in reflection and transmission mode simultaneously. We mentioned that acoustic microscopy is a time-of-flight type of measurement. Time-of-flight uses timing gates, which can be set to capture reflections from specific interfaces located at different depths in the device. The transducers have different frequencies. Low-frequency transducers can penetrate deeper or through the device. Higher frequencies have a shorter penetration depth, but give a better resolution. This is a closer look at what happens inside the device under test. Reflections occur at every interface between the layers of the device. The bottom image shows the reflected signal received as a function of time. By selecting a specific timing gate, as shown by the purple box, we can construct an image of that specific layer. Multiple amplitude scans, or A-scans for short, can be simultaneously acquired and overlaid for comparison. In this example, A-scans at the same location on 7 identical devices are overlaid and shown on the right. Overlaying the scans allows differences or anomalies in the waveforms to be seen. The top right image has only the first scan. The bottom right image superimposes all 7 scans. We were able to see that there were no significant differences in the 7 devices. Reflection mode scans at different depths were performed on 2 QFP packages. The good part is on the left and the failed part is on the right. When looking at the die surface image, we only see delamination at the corners of the failed part on the right. The reflection mode scans were repeated at a lower depth where the leads and paddle are located. We can now see delamination all around the die indicated by the blue arrow. This is an example of how looking at different depths will reveal different things. Now let's look at transmission mode using the same devices from the previous slide. We have a clean transmission image of the reference part seen on the left. However, in the failed part, we see no transmission below the paddle. This is due to delamination below the die interrupting the signal from reaching the detector below. To determine the root cause of the delamination, a cross-section is usually performed and the result viewed under high magnification. These are X-ray images of a flip chip BGA. A plan view image is on the left and a side view is shown on the top right. As the package lid is not in contact with the die, we will need to remove the lid in order to perform acoustic microscopy. We can see from the center of the images that the die is quite small. For this image, the lid has been removed from the chip. Acoustic microscopy shows the bumps and the underfill. The uniformity of the image shows that this device has a good underfill. This is a different device that acoustic microscopy revealed a defective underfill. The light area at the top of the device could be caused by voids or delamination. This image shows that the right side of this flip chip has a delamination inside the die circuitry. Here we were able to see a vertical crack in the die. The acoustic microscopy images on the left showed a possible crack in the die, This was confirmed by SEM view of the cross-section on the right. Here we have a failed die. The image on the left is a software-generated tomographic view of the acoustic microscopy data of the die at different depths. This method is useful in failure analysis because this tomographic view provided us a cross-section look at the device, which enabled us to see that there was a delamination under the die. Once we know that we have a defect and its location, we know to do a cross-section and where to do it. Acoustic microscopy is a quick, non-destructive way to detect that there is a defect. Electron microscopy of a cross-section is a destructive test. However, this was the means to discover the failure mechanism as seen on the image on the right. Scanning acoustic microscopy is useful in counterfeit detection. These 5 parts were selected from a reel at random. We were looking for evidence of counterfeiting. The top image is reflective mode. This image shows delaminations and cracked ice. The bottom image is transmission mode, which shows that 4 of the parts are fully delaminated. When this many parts are bad, they are counterfeit. This is a reflected mode scan of the package surface. Scanning acoustic microscopy detected ghost markings in these black-topped counterfeit parts. The part on the left was soldered by hand. An unsoldered part on the right is shown for comparison. This part was brought to us for failure analysis because it was failing prematurely. The root cause of the failures was determined to be that the parts were delaminating. Even when they passed the test, they had a latent defect that could cause premature failure. It was determined that the delaminations were caused by prolonged high heat of a soldering iron. Mu Analysis is offering a half-day failure analysis course to groups of 5 or more. If you would like to take advantage of this course, please contact us. Mu Analysis services enable manufacturers to reduce design time, reduce returns, and maximize product yields. Thanks for watching.